From a young age, students are taught that the circumference of a circle is 2 times pi times the circle's radius, and that the area of a circle is pi times the radius squared. And this is great, and it is definitely true. But how do we know? Sure, we know that pi is the famed ratio between the diameter and the circumference. But where exactly do these formulas pop up? I want to give a short calculus-based argument of this. First, going to use polar integration to prove the circumference. Then we're going to use, again, one more time, integration to prove the area, integration of these circumferences to form the area. So first, the circumference. So if we're trying to add up small pieces of a circle's circumference here, we know we're going to have to start, we're going to be going polar, so we're going to be adding up a little bit of arc length every time. And what we're going to be adding up is, I'll make it orange here. We're adding up these orange segments, right? So how do we do that? Wrong color. Well, we take the integral from 0 to 2 pi of what? Really, all we're doing is we're taking the radius d theta, right? Because all we're saying is ever happening is that if the circle was, say, twice as long, so this went out twice as far, then there would be twice as much orange arc length, right? If we extended out these sides, for every bit that the radius gets bigger, the arc length gets correspondingly linearly bigger. So the integral from 0 to 2 pi of r d theta, this is going to be equal to r theta from 0 to 2 pi. At 0, it's just going to cancel out. The theta is going to be multiplied, right, by 0. So you just get 2 pi r. Okay, well, there is our circumference. That is the first part of our story. That's why you have the circumference of circles 2 pi r. It's because as the circle gets bigger, you linearly scale 2 pi. Okay, so how does 2 pi r relate to area? Well, similarly, if you were to take small disks, so sum up the circumference of a very small circle times a little bit of width, and then sum up another disk a little bit larger, and then another disk a little bit larger, if you were to sum up all of these little disks' areas, each area, you will eventually get the area of the circle that they make up. And again, to add up infinitely small disks, use an integral. And in this case, it's the integral from 0, the center of the circle, to r, the radius of the circle, the edge of the circle, of the circumference of 2 pi r dr. Now we're going by small changes in radius. And this, we can take out the 2 pi, equals 2 pi times, well, integral of r dr, r squared over 2, from 0 to r. And again, the 0, we'll just make this go to 0. So the only thing we care about is r. And here we find, okay, the 2's cancel out, and we get r plugs into r squared to get r squared, pi r squared. This is why the circumference and area of the circle are what they are. The circumference is a linearly scaled version of the circumference of the unit circle, which is 2 pi by definition. And the area is the integral of small disks of circumference. It's a really interesting connection, I think, between the circumference and the area that you really only see with calculus. The circumference is the derivative of the area, which makes perfect sense, but it eludes at a young age because it is not taught. But it's something that I think is really cool. So there you go.